you some background about the work she's doing. I guess you've been here now for 6 months?
Yeah, I came in January, yeah.
So she's been here for a little while now, and she's, in addition to the work she's doing at the center, she has a whole host of experience from her work before she got here, so she's sharing a wide range of that as well.
Yeah.
Thanks.
So it will, as I told at least one of the group, I don't have any results from my new research here. So it's mostly about the old one, or like a general overview about ice cores. And as already in the tour, if you have questions, just you can ask immediately. You don't have to wait until the end of the talk. Okay, yeah? I have to speak louder? Okay. Sorry. Okay, this is as I showed you before, this is the main places where the ice cores from this group here are from. So Peru, there is one from Alaska, Greenland, European Alps, Kilimanjaro, East Asia, Antarctica, but also here in the Antarctic Peninsula. And there's one from Papua New Guinea. And yeah, these are all over the world, in polar areas and also in low latitudes. So this is a schematic overview about an ice sheet. This is an example from Greenland and Antarctica, so a schematic overview about Greenland or Antarctica. Mountain glaciers are a bit different. So what happens? The snow is falling on the ice sheet, and this is a bit compressed in that direction. So this is this is still in kilometers. So Antarctica is bigger. It's 2,000 kilometers. So this will be 6,000 feet. Is that right? Sure. Yeah. And Greenland is about 500 to 1,000 kilometers in radius. If you know, Greenland is not a sphere, but like east-west, 500, north-south, 1,000. And the thickness is about maximum 10,000 feet in Greenland, and in Antarctica, 15,000 feet. So, sorry? 15. Oh, sorry. 15, sorry. Sorry for my English. Yeah, so in the center, in the inland ice, how we call it, it is snowing, and because it is so cold, the snow stays there and there's no melting. There's some sublimation, so there's some snow going into the air again, but there's no melting because it's so cold. In Greenland last summer there was some melting, but this was really unique. Usually there's no melting. And maybe in Greenland in the future there will be more melting also in the central part because it's getting warmer. But Antarctica is pretty cold. Like summer temperatures are maybe 0 Fahrenheit or something in the central plateau. And then the ice is accumulated here, the snow becomes more compressed and compressed, and the glacier is not at all static, a glacier is moving. So the ice is flowing, and somewhere the ice has to go, and it goes to the side of the glacier. And in Greenland, because it's a bit warmer, there's already melting at the ice edge. And in Antarctica, the ice is flowing into the ocean, and the biggest discharge of ice is with icebergs. So there are big icebergs breaking, and then so the ice is lost again. So this is, the snow is falling on top, and there's some, we call it ablation, loss of ice at the margins of the ice cap. And some icebergs are also in Greenland, but in Antarctica, the iceberg carving is much more important for the discharge of the ice. And one of you asked, where is a good position to drill an ice core? the perfect position would be here, because you have all the layers like very nice on top of each other. You know the snowfall here, and then it's just compressed. If you drill here, you have to take into account that the ice is coming from another place as where you drill. So this would be the perfect site, but there are not so many perfect sites, so you also choose some other sites because of other advantages of the other side. Yeah, this is a mountain glacier. This is a very easy sketch. In principle, it is the same accumulation at the top and ablation, which is melting. There are no icebergs in mountain glaciers, melting in the bottom part. So sometimes, I saw in New Zealand a glacier, there was a big lake and there were sometimes small icebergs falling into the lake. But this is really a minor contribution. And as Jason already sent you, there's a very nice tool. And this is a mountain glacier. The website Jason is not? Oh, okay.
You're just chatting about it.
Okay. You can see this is a mountain glacier, and here it is snowing. It's not shown, but this is the area where it's snowing, or it's snowing everywhere. And here there's the ablation area. So here's accumulation area, there's mass coming to the glacier, and here's ablation area, there's where the glacier loses. And you can try out also at home to change some settings. For example, the average snowfall and the sea level temperature. And these are the two important parameters that change a glacier. So now we change the temperature just by very little. And you see the glacier is retreating. Yeah, but because it's just virtual, we can get it back. And so you see it's growing. And these little dots indicate that it's not only growing, it is also flowing. Now, when it comes to the line, it's in steady state again. And you see these ice particles flowing. So you can see that glaciers are continuously moving. And now we increase the snowfall. And the glacier is growing. So you can play with that. And up here, the bear, you can go even more. And now we do an ice age. So we decrease the temperature by 10 Fahrenheit. And the glacier is growing a lot. Whoops. Doesn't want. Okay, you can see it in small. I don't know why it is not moving. You can see it in small that it's even more growing. And now we get it back to an interglacial, which is a warm stage. And it's retreating again. I do it a bit warmer that it retreats faster. Just to get it back into the window. I don't know why it is. Yeah. And here you can see that these black dots indicate some debris that is left from the glacier. And as the plant that I explained you downstairs, if you find those leftovers that the glacier uncovered, you can date it, or you can see where the glacier has been or where it wasn't. So this is a nice tool where you can also put some markers on the glacier to see how fast it moves. And that's really done for science, that we put a pole with a flag at some point in the glacier. We measure the GPS position. We measure how far the stake is out of the ice. And then you go there next year and the year after or whatever. After a while, you measure again the position, so you can see how far the glacier moved. And you measure the height of the stick, so you can see how much snow there was, how much accumulation. And usually you do not use just only one stick, and you do not go only there 1 year, but you use a range of sticks and go there several times. Jason sent you the link. You can play with it. Very nice tool. Okay, what is how does the ice core and the ice sheet, how does it develop? You have the snow. In the upper part, you have the so-called firn. Firn is like very coarse material. The air can still circulate, and then it becomes denser and denser and denser. And then at a certain depth, you have the so-called bubble close-off. That's where the bubbles close and the air is entrapped into the ice. This is 260 feet, sorry. And that's what you saw in the ice core that we saw downstairs, that there are little bubbles in the ice core. And here you have, for all of you who didn't see the bubbles in the real ice core, you have a picture of the bubbles here. So that's how they look like. This is illuminated and against the black surface. Here, this is a computer tomograph CT image, like what you also do in medicine, but you can also do that with firn, so you can see how much air and how much snow is there to investigate how the compression of the ice takes place. And this compression of the ice is very important if you want to do interpretation of the bubbles. You have to know how those bubbles got into the ice. And this is ice crystals. Ice is not a homogeneous material. There are a lot of crystals, and with a special technique, with a special lighting, you can color them in different colors. So each color is a different crystal. If you would just look them here in the room or in the cold room, they would be all transparent, all ice. But with a different illumination, you can get them in cross-polarized light, if you know what that is. You can get different colors for the crystals, and you can measure the size of the crystals and the orientation, and this is important for the glacier flowing. This is something what we can see in the ice core. As I told you, we can measure dust particles, we can see storminess, we can measure the gases out of the bubbles, and we have a record of the gases in the atmosphere. We can measure sea spray, we can measure volcanic eruptions, and also anthropogenic pollutions like lead or sulfate or whatever. This is an overview about the deep drillings in Antarctica. WISE, West Antarctic Ice Sheet Divide, is a US drilling that was the latest one. There are other US drillings here. Dome C and Droning Maudland are European drillings. Dome Fuji is a Japanese drilling. There's Vostok here, which is a Russian drilling, and Italian drilling. So there are many countries involved, and most of the drillings are international collaborations. Like a big country like the US, they have the power to do their own drilling, but like Europe, many countries work together to bring all the money, all the manpower, all the logistics together to make these drillings. And there are also many drillings on the Antarctic Peninsula, but they are not like so deep drillings because the ice is not so thick. This is Greenland. The latest drilling is Neem. It's for North Eam, and Eam is the warm period, the penultimate warm period. Now we live in a warm period. Before there was a cold period, the last glacier, and before that there was another warm period. And this is the so-called Eemian, and Neem is for North Eemian because it's the northern hemisphere. And the goal was to drill the Eemian, but the ice was folded. We got the Eemian, but we got it like upside down. So there was first some science to do to make a good dating on that core. But it was successful. And as you can also see, here's a lot of land exposed. So the ice is melting here a lot, and here in the north there and in these fjords there might be some iceberg discharge. Now I want to show you some pictures from an Antarctic station, and this is from the Conan station. It's because I have been there. All the countries that were involved in those projects, and they're like 2 inches of snow here each year and 1 inch of snow in Dome Sea. So very little snow, and this is in comparison to other areas, this would be a desert. So there's less precipitation in Dome Sea than in the Sahara. So it's really, really dry, very little snow accumulation. This is a picture. This is living quarters. There's a workshop, there's a kitchen, there's like a community room, there's a room with a washing machine, a bathroom, a shower, and there are 2 living quarters also with beds, but they are only the camp leader, the doctor, the cook. So this more, like the cook has to go every morning very early to the kitchen, so he gets a place to sleep here. And all the other people, scientists and so on, they live in small huts that are a bit like maybe a 2-minute walk from this main station. And here is the entrance to the drill station. So the drilling is below the surface, because then you're much more, if there's a storm coming and the you are not affected by the storm, the temperature is more stable, so there are better conditions below the ice than above the ice to do a drilling. This is a fuel tank. You need a lot of fuel. This is very important, and the generator to generate all the heat and all the electricity you need. And this crane is for the freshwater production. And this is all the water that is used. There was snow before, and it's shoveled in a big bag and then put into a snow melter, and it's melted, and then this is used for drinking and for showering and for cooking and washing and everything you need water for. So that's also a reason why we have to pay a lot of attention to keep the area clean, especially the area where we get the water from, because when we drink it afterwards, we want not that whatever, a caterpillar went through it or a lot of people were walking through it. So you want clean water, and therefore it's your own interest to have it clean. This is below. It's a bit hard to see. This is the drill. As I told you, it's pretty long. And this is now at the moment where it's coming up or going down, then it's tilted. And at the surface, it's tilted like this, back. And here the core can be extracted. Here the core barrel will be put here, and then the ice core will be extracted and carried to the side, and here it will be measured and cut into pieces and so on. And then the chips will be extracted, everything will be cleaned, checked that everything is fine. It will be mounted together again and then back into the hole. And here you see the winch. It's a big winch which has all the cable to send the drill back down. There's a small hut where the driller, when he's driving the drill up and down, can be a little bit warm, because it's even 20 degrees colder than in the cold room it's there. So it's like minus 40. This is a picture. Here you can see the cutters where the core is cut with, and you can also see nicely the structures of the ice, the different crystals. And then it is cut into different pieces. This is an example where one project I was working in was cut in this way. Other projects are cut in completely different ways. What is important is that always one piece is kept for the archive. So if you drill a core, generally you would not use all of the ice from the beginning. You would have something for the archive. For example, this half core that you saw in the cold room was the archive. It was drilled in 97, but now I came and we have a new technique with the ICP-MS. We can measure all these trace elements. So this is a good reason to say, okay, I would like to have something from the archive, and I do some new analysis that were not possible in that time to use a piece of the archive. But of course, I'm not allowed to use all the archive. So I have to put something back to the freezer if somebody else comes later and says, you know, now I have a really new technique, and I would use also something for the archive. So this is like oxygen isotopes. Beryllium-10 is for solar activity and the geomagnetic field. Gases, dust, CO2 are the greenhouse gases. Thin sections is for physical properties, for the bubble size, bubble distribution, crystal distribution, and so on. And this is CFAs, continuous flow analysis, is for major ions and like other impurities that are in the ice core. And what we get out of it are those those plots. And here we already have a dating. This is the oldest ice, it's 800,000 years old. And what you can see is that in the upper part is a temperature, and in the lower part is CO2. And always if the temperature was high, the CO2 was also high. And if the temperature was low, the CO2 was also low. And the dust was the other way around. When it was cold, we have high dust concentrations. So it was drier, the sea level was lower, we had more land exposed, it was windier. And if it was warm, we have less dust. So then having those curves, we sit in front of it, and then we do our interpretation on it. This is more or less the same. High temperature, this is methane, greenhouse gas, and CO2. And when it was warm, always the methane and CO2 concentration was high. And this was over the last 800,000 years. That's the range that we can cover with the ice cores at the moment. And just to comparison, where we are today. So this is methane. So over the last 800,000 years, we were between 400 and 800 ppb, which is a unit. And now we are at 750, so far above what we found ever before in ice cores. And okay, the CO2 somehow got lost, but the CO2 is at the moment at 400. So we were between 180 and 280 for the last 800,000 years. And now we are at 200, which would be approximately here. So much higher than before in the last 800,000 years. So this is what, at least to one group I told before. This is sulfate. And you can measure sulfate emissions. This is the acid rain that was a big topic several years ago. And this is a Greenlandic ice core. And the measurements from the Greenlandic ice core is this line. And the emissions from the US in crosses and from Eurasia in the dots. And you can see the emissions rose. And immediately we could see it in the ice cores as well. And the good news is that because the emission decreased, there were some regulations about the car emissions should be reduced. And also it was reduced. We can see the reduction already in the ice cores. And you can see that in the US it started first, so then came the European bump. But now Europe is also on the good way. And in Asia, this is an Asian ice core with the emissions. And there's no, the emissions are still rising. And yeah, we can still see it in the ice core that there, of course, the economy is rising. There are much more cars, and yeah, therefore there's still the rising. trend. So that was my talk, and if you have any question, you're very welcome.